Okay, so yesterday, actually, we have finished this hello world example. Okay, so in this model, we have this single event going on. Okay, so now today we are going to extend. Okay, this is a hello world model, so I can show you some more things. Okay, so what the simulation can be. Okay, what the simulation can do. Okay, so the first I will start to ask you this question. Okay, is that in the real world, okay, in the real world, the actually it will seldom happen that okay, if you want to like schedule some things every maybe 1 minute or 1 second, 5 seconds, but in the real practice, okay, so I mean the real time for these things to happen, for this event to be invoked, is actually affected by a lot of the uncontrollable noise or factors, right? So, I mean, if everything is planned, is actually according to the plan, so then everything will be fixed. In that case, I think the simulation will not be useful, okay? Because everything is according to plan. So we just need to use a mathematical way to calculate the happening time of all the events. All the things can be actually estimated precisely. But the things become complex if the time point for those events to happen is uncontrollable or maybe affected by some factors which are unknown, okay, not analyzable. So in that case, actually the randomness will become very important. Okay, let me take one example. Is now is that we have a 5 seconds. Every 5 seconds, we actually come up with this event called a hello world. Okay, but in realities, this might not be 5 seconds. We schedule something, but because of the maybe some of the problem like the monitor got some delay, the processing, computer processing the data, okay, because of heavy load of the computational work. So this 5 seconds may sometimes become 6 seconds, sometimes can be 4 seconds, 7 seconds, right? So this time is actually can be random. So in that case, instead of to have a single time randomness here, so what we are going to have is we use a random distribution to generate a random time delay, okay, for this event to happen. So in that case, what should we do? We'll use a random distribution. Okay, so here I'll use this one. I will demo to you that we can actually use the uses the distribution dot. Maybe I will just use an exponential distribution as illustration purpose. So what is the distribution? What is exponential distribution? Maybe we can have a separate session to discuss about that. But now we just treat this one as like one way to generate a random number, meaning that each time when we generate a number, it will be different, okay? But actually we have a certain criteria is to see that when we generate a number, so in average, I want the mean to be 5 seconds. Okay, so this is what we can do. But because of this O2DES distribution namespace, I can actually remove it here. Okay, but rather I will add it at the top of this file. Okay, so you see that. Sorry, it's not this one, but rather it's as net. Okay, the dot distribution. Okay, so we're actually using this exponential distribution to generate some number, then use this number to delay the my event, the scheduling of my events. But we're actually putting this number here, this time span here, okay, just to make sure that in average, it will be 5 seconds. Okay. And also you may ask, what does this mean? Default RS. The RS is actually a random stream. Okay, it's a random stream. So here we are saying that when we generate the sum of the random number, so we want it to according to certain random stream. Okay, the random stream is actually literally it's like it's a stream of the random number. Okay, so it's actually a list of the number so that the first time you call to generate one number, it will get the first number for you. So if it's the second time, it will give the second number to you. But you may say that, wow, you see this as random, but if you do in this way, is this really random? Okay, so of course, it's not real random in the sense that we understand from the real life, but it's a random in the sense that actually, if you look at the first number, second number, third number, does not really have a trend for you to predict what is a false number. Okay, so actually this is the meaning of the random. But you see that why do we need to have a fixed random stream here for you to generate this number? It's because now we are doing some analysis. So meaning that we are making a program so that we need to analyze based on result of this program, and it's also is that sometimes when there's a problem, we need to debug what is happening in the program. So just imagine that if you run the program at the second time, the third time, every time they show you a different result. So if there's any bug, how do you know where the bug is? Okay, maybe the bug is just caused by this randomness. So the next time, if it's a totally random, then we just cannot find the bugs anymore. Okay, so this is actually why we need to have used this concept of the random stream to make sure that every time you generate a number, it's actually give you a same sequence of the number. Okay, although you cannot predict the trend, but next time you repeat again, it will give you the same trajectory, will give the same result, exactly the same result. So in that case, you can analyze and also doing debugging if necessary. Okay, so actually this is a random stream we can use. So now in the O2DES framework, you just need to put a default RS, default random stream. So that will be good enough. So later I will illustrate to you that what are the other things we can use here, but now it's just to bear in mind, if no other consideration, you just put, whenever you need to come up with a random number, generate a random number, just put in this default random stream, okay, inside the distribution sampling. Okay, so by now, any questions? If not, maybe let's just continue the program and see what will happen. Okay, so when we change back to the program, you see that here actually we're running for 40 days. I think this might not be something we want because it's too long. So what we can have is maybe just a 1 hour. No, sorry, maybe just 1 minute. So totally we'll have 10 minutes. Okay, then we remove these things. So we'll continue to run for 10 minutes. Okay. But this time you can see that, okay, if you look at the time interval between the two events, okay, now we see that it's not fixed anymore. It's not every two events is divided by 5 seconds, but rather you can see the first one is about 1 second, 1 second, 1 second, then 3 seconds. Then this one will be the 8 seconds, 3 seconds, etc. You can see that each time the new event comes, the interval between the two events, consecutive events, is actually different. Okay. Then we can see that, but although we can see that all the random are different, but if you count the total number of the events here, if you look at the total number of events here, if you look at average time interval, it will be 5 seconds. Okay, believe it or not. Okay, so if you count those numbers until here, it will be some number around, now you have 10 minutes, right? 10 minutes, you have a 600 seconds divided by 5, so we'll have 120 events. So if you count how many hello words, I'm not saying it's exactly 120 lines, but actually there's some number around that level, okay? But if you repeat this experiment many times, for example, or maybe you just enlarge the simulation run, maybe to 10 hours, 10 days, or 10 years, okay, then if you calculate the number of events generated, you will see that the average time interval is actually approaching 5 seconds. Okay, so this is some things about to let you have a basic understanding of this random time generation. Okay, but of course here we are using exponential distribution. I mean, if you have some of the knowledge about the statistics, so you also know that there might be other distributions, random distribution you can use. So in that case, you can just use a different triangular or whatever, or maybe Poisson. Okay, so actually use other distribution to generate this random number. Okay, so by now, any questions?
No.
Okay, so if no questions, let's continue to the next one. Okay, so just now I said that one of the interesting problem is that after running the simulation, probably the what we want to observe is to see that, okay, how many events hello world have been generated. So for example, if you just run these things to the end, okay, what you will see is just a number of message printed out from here, but you do not really know that how many hello words have been printed out. Okay, so in that case, what should we do? So we need some like a parameter, okay, to be built inside the simulation for us to count how many lines has been printed out. Okay, so in that case, what we can do is here inside the sandbox, I created one property maybe called a count. Okay, so I have a get and set, meaning that we can set a value to the count. We can also get the value from this account. Then I put this number as public property, okay, as a public property, okay. So in that case, whenever there's a my event executed, not only to output this message to the console, but also I doing another things, which actually count plus plus. I let this account to be +1. Okay, so this is what the event will do. It's basically collecting the count of how many hello words has been printed out. Okay, then how do we use this message is that at the end of the simulation run, okay, so we just need to like output this number to see that model dot count. Okay, we just need to print out this message, okay, to check that what is the value of these models for the count. Okay, so now, just now I said it's around the 120, right? So here we actually observe 139. It's somewhere like around the 120, but now it's because the simulation we run is not long enough. So you see that still like a 20, like a 19 difference. Okay, but if we make it longer, then you can see that this average number we are approaching to what we predicted. For example, if you like put a 20, I cannot guarantee because everything is random. But I mean, if we make it longer, then the 240, you can see that we double the run length and the difference actually reduced to 12. I mean, from the expected value. Okay, so here you can see that we actually have this count. Okay, here to help us to collect the running of the simulation. Okay, collect some of the information while running the simulation. But also I want to say that the way we write in this way is not secure, in the way that you see that what happened if I just mistakenly did something like this, model.count, okay, equals to 15. Okay, if we do this thing, then what you expect to see at the end of the simulation, instead of like a 250 something, we actually have this 15, but this is not something we want. If it's set in this way, it's meaning that we did something wrong. You cannot set some properties inside the simulation without really running the simulation, right? So this is some things we want to avoid. How to avoid these things? We set this as setter to be private. Although the count is some of the public properties, but because we only allow this value to be added within the simulation, so we set this as a private. So what happens if you jump to the program? You will say, this statement is wrong. You cannot anyhow like add a value, set a value to these properties in the simulation model, because this property can only be set within the simulation model. Okay, so this is how we actually avoid this setting, and also to make it like a better behavior is that here we want to specify what is the initial value for this count will be 0. Okay, so although that if you don't set anything, by default the C# will set the initial value to be 0, but it's just like to make sure this value is really something we want, because sometimes I mean the value we want to set is, instead of 0, we want to be like other value. For example, here is that every time I do not really want to count +1, what I'm doing is I times these things by 1.1 something. Okay, so in this case, this then in that case it should be double. Okay, so if we like do this multiplication, then meaning that initial value cannot be 0, but instead it should be 1. So actually this is a way to say that when you define some property, you need to understand that what is like a default, okay, properties, default value of these properties. So the better way is just explicitly indicate what is the initial value. Then this initial value is actually the same as you indicated here, okay, to see that this count equals to 0. Okay, so this actually have the same result. Okay, so this actually illustrates actually one of the important things in the simulation modeling is that what is this properties regarding the simulation of O2DES model. So this one we actually call this one as a dynamic property. Okay, this is actually a dynamic property of the simulation model. Why dynamic? Because while the simulation is running, this thing change in a dynamic way. Okay, from a time to time. Okay, so this is why this is called a dynamic properties of the simulation model. Okay, but you see that, okay, this is the dynamic properties. So how about the static properties? Okay, so static property is actually meaning those value does not change, okay, from the simulation wrong. So what is the static properties from here? So anyone can tell me what are the static properties you observe from here? Although I did not set a static parameter, static properties here, but can you see from this setting which value is actually not changed throughout the simulation running? Anyone can answer?
Like the clock time, sir? Can it be the static property or it is also changing with
Which line?
time?
Which line?
Uh, Sir, like static property, uh, another guess different. Like when
Tell
we are
me which
giving,
line. Tell me which line are you referring to?
okay, okay. Yeah, yeah, yeah.
Which,
Line number 22, when we are giving exponential sample uh,
yes,
from seconds 5. So at that time, uh, the time which we mention the mean uh,
this one, right? The
5,
time span, the
yeah, yeah,
5 seconds,
yeah,
right? Yeah.
yeah, yeah.
Yeah, that's correct. That's correct. So this 5 seconds is actually something did not change, okay, across the time. Why? It's because this is a parameter we set for this distribution. Then we are actually using the same parameter from time to time. So it's become a static property. So instead of writing in this way, another way is to put it as static properties. So maybe you call this one as a time span, the type. Then we call this as a mean inter events time. So put this one as a mean inter events time. Okay, then we can actually set this one to time span from seconds 5. We set a value here. Then in this part, we can just call this mean inter events time. Okay, then you can see that, may I ask a question whether we can like set this as a private? Whether we can set this as a private?
Yes, I think can.
Yes. Yeah, then, okay, when we want to like deliver this toy to you, if I deliver this toys to you, okay, so now is that I want to, instead of every time I run for 5 seconds, but now if you want to change the model setting, for example, it's like, this is a toy, okay, then you want to write a different button, if you want to control in a different way, then you can see that if you like set a private setter, then you actually have a difficulties of playing with that, okay? So in that case, what we are going to do is we actually can put a parameter here under the model. When at the time I construct this model, so I will put a time span here to be mean inter events time. Okay. Then what we are going to do is we'll let this mean inter events time to be the parameter. Okay. Okay. So we can actually get this initial values, the default value from here to here. Okay. So I will explain. So what does this mean? Okay, sorry, I think cannot do this. Cannot do this. Okay, so in that case is that when we construct a model, okay, you can see that this is wrong, right? It's because the model actually expect parameter to set this toy, okay, to set this sandbox. Okay, you need to tell me that what is the inter events time you want to run. So in this case, I will just run for 5 seconds. Okay, then we can see that when we run this model, we actually come up with a different number, the 252. But if we set this to 1, okay, then we run for like 20 minutes. Okay, you can see that we observe a different number of the events executed here. Okay, so here you see that this actually, we call this actually a configuration of the model. Okay, this parameter, which is here, is actually called as a configuration of the model. Okay, and this actually called a static parameter. This actually is the static properties. The static property doesn't mean that we cannot change it at all, okay? But rather is to see that while the simulation is running, this value will not change. Okay, this value will not change. So usually when we write the program, what we do is we have this, we put a statics, then we have this end range, then we have another one, region, we call the dynamics, and region. Okay, so we use this one for the static property and the dynamic properties. Okay, so okay, by now any questions?
No.
No, sir.
Okay, so one more thing that I want to show you is that, okay, so just now we said about the random stream. Okay, random stream is actually meaning that if you repeat the simulation run many times, every time will give you the same result. For example, if you don't believe, I just change this back to 5. Just now we observed 252, right? So if I run this again, I will got a 252 again. So whenever, I mean, how many times you run it, it will always give you this 252. But you may ask that is that, okay, you said that your simulation is actually a random, but how can we see the randomness? Okay, yeah, we understood that you want to like control the way the simulation is run so that it's analyzable. Okay, but the thing is, if we want to randomize it, okay, how can we do it? So in that case, we actually rely on these things. So we look back to this random stream. So this is a call to control the randomness of this simulation execution, okay? And we'll see that this random stream is controlled by the random seed, okay? So how this random seed is used, I will show you. Just now I'm using this model constructor, okay? When we construct this sandbox, okay, I'm just defining the constructor like this. I initialize the, okay, actually I should better to put this first up because it's a static property. I set these static properties based on the parameter passing. I set the dynamic properties, okay, and also I schedule some of the first of the initial events. Okay, so basically these are the main things simulation constructor need to do. But what if we want to like have some impact on the random stream? What should we do? So instead of constructing the model from scratch, what we do is we let it to extend the base, okay, the base constructor, the constructor of the parent class, meaning that this sandbox actually has its own constructor, which can be called by here. And this constructor actually come up with a parameter called a seed. So if we do not do so, by default, okay, the constructor was used and the seed is set as 0. But if we set this one, we can actually specifically change the value here. How do we do this? We let this seed to be some parameter to be passing, and we use this seed parameter to pass to the parent class to construct the parent class, construct the sandbox, meaning that all the default random stream is actually based on this seed passing. So in that case, here we actually will require another parameter. We call the seed 0. So actually the same as just put 0 here. Okay, it's just like in the C# syntax. If you want to increase readability of your program, you can like put a parameter name here followed by the colon. Then you can see that okay, so this is actually the seed. It's the same effect if you set to 0. So if you run, we can see that it's actually 252 again. But we can actually change the random seed to be another value. Probably just change to 1. You will see that this number will be very different, 232. Okay, so this is the way we can play with random seed. So if you want to try to increase to another 1, change the seed to another 1, you'll see that, okay, it's a 230 instead. So if you change a different seed, then we come up with a different result. So this is a different seed. Okay, when we run the simulation for different seed. So this one we also call another name in the simulation-based optimization. We call this a random, the simulation replication. So this one is called a one replication with a random seed. With the one random seed, we have a one replication. So if you want to have a different random seed, then we have a different replications. Okay, for example, now if I want to run my simulation for 10 replication, so what do? We use this one, we call a seed equals to 0. Then we range from 0 to 10, actually to 9. Okay, then each time, okay, we use a different random seed from 0 to 9. To here. Okay, you set the seed here. Okay, then you can see that you run this simulation for different random seed. Actually, yeah, you can see that it's actually run many times. Okay, each time it's finished. Okay, output result, then continue. So in this case, we actually run a lot of the replications. Okay, the 10 different replications. Then we can observe the different result at the end of it, at the end of the simulation. So this is how we can play with the random seed. Okay, so by now, any questions?
No, sir.
Okay.
Sir, just one question, like about the base class, sir. Uh, uh, can you explain little more about it? From where you took the random sheet in the model.cs? Yeah, if you don't specify the base class, it will not work.
Okay, if you do not specify this base class,
Yeah.
okay, because this default random stream is something protected, okay, at the base class. So you cannot do so to see that default random stream equals to new random, then seed. Okay, you cannot do so because this is something that only read only. It's read only, okay, for all the inherited classes. Okay, so you cannot set a new value here. So the only way you can set a different random stream, default random stream, is to do this
Okay.
using the base class.
Okay.
Okay,
Okay.
but I because this is actually all the things is actually we program it by ourselves. So actually you can find an alternative way, which is you can actually have some like a random string which are not default one. So you just say, okay, this is random one. Okay, so yeah, maybe I just call it. Maybe it's yeah, because it's private, so I use this one. So random one. So here instead of using the base class, so what we do is we set this random one to be some new random string by using this state. This is also possible. So in that case here, you can just use a random one. I mean, this will have a same effect, exactly the same effect.
Yes.
It
Yes.
just, this one is a little bit troublesome. Okay, and usually, so if I just want to extend a little bit on how we play with the random stream, is that, for example, like sometimes we want to have a separate, we want to have independent random streams, different independent random streams in the simulation. For example, we have this queuing system. We have arrival customer. We have the service. Okay, the server. Okay, so we want to like control the service rate, the service service time and arrival time using a different random string. So in that case, how do we do? So the way we do that is that we can construct a different random string S1 and S2. Okay, so I use a different random string. Okay, then here is that I still use this one to have a default random string. Okay, but what we do here is we set a different random string to this RS1 and RS2. Okay, but we're using a different random seed. Okay, for the RS1, RS2, then this random seed is randomly generated from the default random string. Okay, so either default rs dot next. So this will generate one integer from the default random string. Then we have this one to have another random string. Then instead of using default random string, I'm using this rs1. Okay, so this actually to make sure that whenever we generate the new events, we're based on this random string. So if now later we have another events for the IS2, okay, then these two stream will be independent from each other. Okay, so meaning that if you change a server, then the way we generate arrival of the customer will still be the same. So this actually is sometimes we call this a random common random number approach to make sure that a certain part of the simulation is actually consistent between the different solutions, the different comparison. Okay, so this is how we can do it. Then you can see that this default random stream only be used 2 times. Okay, to give the seed for first random stream, give the seed for second random stream. Then whenever you change, I mean for the like service or arrival stream, actually does not affect these 2 sequence. As long as this 2 sequence is not affected, then a single random seed will give you the same random stream 1 and the same random stream 2. Okay, so this is how you use a single random seed to control a different random stream in the simulation. Okay, so I think here we just undo all those things so that we make the base model simple. Okay, so this is some things I want to show you now. Okay, we want to show you now. Okay, yeah.
Yes, sir. Yes, sir.
Okay, so I think we actually most of finished what is planned for today, but I think I just want to add a little bit more, okay, for you to understand maybe some of the extended concept of the discrete. Oh, okay, let's do this thing. I think there's still like one more things we haven't go through is that how do we differentiate a discrete time simulation and a discrete event simulation? Okay, so I think I use one of the drawing to showing what I want you to model, so we can consider this modeling by using a different approach. Okay, so you can see that this might be something we're going to model. Okay, so we can see that, for example, now we have like 100 person at the one places. Then, I mean, every certain times we actually want to move one person from the left-hand side to the right-hand side. Okay, so for example, in average, like what we are saying here is every 5 seconds. Okay, every 5 seconds or mean, or maybe we just set as the mean inter events time. So every mean inter event time, we're actually moving one person from the left-hand side to the right-hand side. Okay, so in that case, okay, let's model. Let's try to model is what I mean, how does this looks like? Okay, so in this case, what we do is that at the beginning, maybe we will set another dynamic. I mean, instead of the count, we'll see that this will become like the number of person, number on the left. Okay, the number on the left. Okay, then at the beginning, we'll set this one to be 100. Okay. So when this event happens, so what we do is we'll move this number on the left. Maybe I think the same thing now, we'll have the number on the right. Okay. At the beginning, we'll set the initial value for the number on the left and number on the right to be 100 and 0. Okay, so every time when this event happens, what we do is we'll let this number on the left to be -1 and the number on the right to be +1. Okay, but however, there's actually a condition to see that if the number on the left, okay, then we'll see that only when the number of the left is more than 1, is larger than 1, then I will schedule the next events. Okay, you understood this? So that's when all the 100, let me move to the right. Okay, then this simulation will stop. Okay, this simulation will stop. Okay, so in that case, let's run and to see what happening. But before we run here, instead of saying the hello world, I'm going to write in this way. So left actually have this number called a number on the left, and also the other things is actually number on the right. Okay, so in that case, let's run the simulation. I will show you. Okay, something wrong. Okay, it's a count. So I shouldn't like output a count at the beginning and also at the end. And also that's instead of running for 20 times each 1 minute. So probably I just run for okay, so I think in this way I will teach you another way of running a simulation, because now the problem is that by moving this 100% from the left to the right, I do not really know that how much time it takes, right? So in that case, I want to run the simulation until the end of the world, meaning that when all the things move to the right, then there's no more events in the world, in the simulation world, then we stop. So in that case, I will show you another way of doing the simulation. Is actually to let's spread this out. I just use a random seed of 0. I just use a random seed of 0. Okay, but here instead of giving a specific time, what we do is we do this while model run 1, then do nothing. Okay, let me explain what does this mean. Model run 1. Okay, so if you still remember what we talked about yesterday, so this actually meaning that I will run the first event of this model, right? So we actually have a returning. So this one will actually return a Boolean value. Okay, so this Boolean value is actually to tell that whether the simulation is able to be continued. Okay, in the sense that whether there's any future event, okay, in the future event list. So this will be a model.run. So what this thing will return. Okay, so in the case that if the model.run return true, meaning that this model can be continued. So in that case, we'll repeat these things again. Okay, so in that case, we'll see that this model.run will repeat again until it return false, meaning that there's no more events, okay, inside the future event list, meaning that, okay, this thing actually reached, meaning the number of on the left is larger than, sorry, it's larger than 0. Is equals to 0, okay, then in that case, the simulation will not schedule any future event list, then the simulation world is actually terminated. Okay, so in that case, you can see this is what is happening now. Okay, you can see that on the left is starting from 99, because this is already after the first moving to move 1, 2, 3, 4 until all of them move to the right. Okay, so here we can see that this is actually a so-called a discrete event simulation. While you actually are moving all the like particle or the person from left to right, right? You do not really care about what happening between the two events. Okay, you do not really cares about what happens between 0 second to 1, or maybe from like this will be more obvious from the 3 to 6. what happens in the 4 second, 5 second does not matter. Okay, so after this, immediately I'm looking into the next time when this moving happens. Okay, so this actually called a discrete event simulation. So if you look into the result, is that you can see that the first is all the results showing is a discrete. Okay, and also in the discrete in the sense that it's a discrete according to the events. Okay, so how many discrete lines you have equals to number of events we have. But what is about the line, the time, how much time had passed, does not matter. Okay, as long as the 100 events, then you 100 lines. So I just want to show you one example is that if I could change this one to maybe 20 seconds, it takes longer, right? It takes a longer time to run. But if you observe the number of events, it will still be 100 lines. Okay, so it's a discrete based on the event. So this is called a discrete event simulation. Then you may ask another question: is what is a discrete time distribution? Discrete time simulation. I will show you this. Let's still come back to this graph. Okay, so if it's a discrete time, okay, then what we will do is that we will see that okay, actually there will be always a sum of the assumption of how it's actually flow from the left to the right. Okay, how the flow will flow from the left and right. So in a discrete time simulation, meaning that it's not a discrete event. So actually there's assumption that the changing of the status is a continuous. Okay, the changing, I mean, this actually is some like a concept at the back end is if it's a discrete time simulation, usually we're using it to simulate, to approximate a continuous process, okay? Otherwise, if you use a discrete time to come up with a discrete event system, then it's actually a wasting of the effort. So usually when we come up with a discrete time, it's because the backend system we assume is a continuous, so that we use a discrete time to approximate the state change of this continuous process. Okay, so in that case, if you have 100 at the left and 0 on the right, so it's meaning that when we have this like 20 seconds, it's actually meaning that by average, every 20 seconds, there will be like one flow from the left to the right. So in the sense that if you want to calculate the flow rate, it will be every second will be 1/20. Okay, it will be like 1 over this number of seconds. Okay, so they will be the flow rate, the flow from the left and to the right. So what we do here, so in that case, if you like assume this a continuous flow, so if you want to do the simulation in this way, so what we do is that the first is whenever this number of the left is larger than 0, meaning we still got some stock on the left, what we do is we'll schedule an event, but this event will be always after a discrete time interval. Okay, so at this time, maybe we just put as 1 second. Okay, so this will be the discrete time interval. Like every 1 second, we're actually updating the system. So when we're updating the system, what we do is actually we look at the number on the left, we'll divide it by how much, I mean, customer or maybe stock have been moved from the left to the right during this 1 second. Okay, so in that case will be we use this one. Okay, this is a mean inter events time. Also now we should not like say mean inter event time, but actually is a inverse of the flow rate. But now that's just a temporary using this one. We look at how many seconds we have, okay, for each move. Then we use this 1 divided by 1.0 because it will be a decimal number. And also the number of left will be decimal as well. Okay, so we actually put at double. This one we also put as double. Okay, so this will be maybe I just call this one as a quantity of moving from the left to the right. So I set this a quantity to be 1 over the total number of the seconds. Okay, I mean between each whole unit move. Okay, so this will be a quantity move within that small time interval. Then we use a number of left. We use the quantity to cut it, to reduce it from the stock on the left. then we're actually using this one to be added to the right. Okay. So this is something we can do. Then we'll see that what is happening. Okay, you can see that we actually that takes like 33 minutes. Yeah, maybe because what is the number we set here? 20 seconds. Yeah, maybe just 5 seconds. Okay, then it'll be shorter. Then you can see that in total, it actually takes the 8 minutes and 19 seconds to move all the amounts from the left to the right. But basically, you can actually see that this number will be, this time should be the similar as a discrete event simulation just now. It should be around the same amount at the time. But here you can see that how many lines we have printed out. It's actually according to the time. Okay, it's actually according to the time. So if you have 8 minutes and 19 seconds, meaning that all the 8 times 60, like 480, so 499. How many seconds we have? Yeah, 499, so 500. Actually, 500 seconds. Yes, totally is 100 unit. So for all the 500 seconds, each second, they're actually a one output. So in the sense that if you want to increase this time to double the time, the running time, by slow down the flow rate, then we can see that we actually have a more number of lines, okay? More lines to be printed out. This is because the simulation is based on the discrete time. Then what is a discrete time interval? Is actually this 1 second. It's actually this 1 second. Okay, so you see that there's a no event concept here, but it's actually it's a continuous. We're actually approximating a continuous flow, but because in the computer, in the programming world, we cannot really do continuous, so that's why we discretize a time point into a small interval to be 1 second. Then we use it one to approximate what is happening in the systems. Okay, so you can say every 1 second, actually there's a slightly change, okay, in the values. Okay, so this actually differentiate the discrete time simulation from the discrete event simulation. Then to summarize is discrete event simulation, sometimes execution is more like efficient, okay, in terms of a computational effort, the budget we need, because they only need to consider the number of events, do not need to consider the time we're going to run. And also, but actually it has some like a limitation, meaning that if the system is provided that this is a system actually include the discrete event to be happening inside a system. But this is actually very common in most of the industrial systems. So if you look into the port, we look into the warehouse, or maybe we look into a general concept of the industry where a lot of like a man-made or man-designed procedure inside. So actually they are event-based, they are event-driven. But if we look into some kind of the natural system or even an ecosystem, like a very large scale system, you consider many like entities flow inside like a city, urban traffic in a city. So if we want to model a problem in that kind of scale, then usually we actually treat the flow of entities within such system is actually continuous. Another example is that if you want to simulate like a pandemic, like a COVID-19 situation, then many of the study actually using the continuous simulation. They use a discrete time approximation for the simulation and the involving of the status variable. So in that case, they use a discrete time simulation. Okay, so this actually to differentiate these two. So any problem from you for this?
Sir, just now you told about the future event list. So the future event list is present in the program.cs where you have written model.run. That is the future event list. That
I,
comes.
I think currently, I mean, at this stage, we do not need to like bother about the future event list because
Okay.
here you just need to imagine that if there's a no event scheduled, okay, in
Okay.
the simulation world, then the simulation will stop. Or maybe, not maybe, is that if there's no, the simulation will not stop, but when you run something, it will return false to say that the simulation doesn't know how to continue. So this is actually also something special for discrete event simulation, meaning that if there's no event ahead, then the simulation will just don't know how to move on, right? Because it's different from a discrete time simulation. If there's nothing ahead, so all the state variable just remain the same. I just update the clock, I mean another discrete time interval. So then this will going on and on, okay, without the stop. Okay, so this actually for discrete time simulation, you know that what is the next time point you are looking for. But discrete event simulation is different. What is the next cross time of this simulation really depends on the clock time of the next event. So if there's no event schedule in the future, then the simulation will just pause somewhere. It will just return false to let the controller or maybe the toy player to decide what do you do with this simulation, because now within a simulation, I don't know how to proceed. Okay, so I think this is the idea. You only need to know about this idea. That will be good enough for this session.
Okay, okay, sir.
Okay.
Sir, yes, sir. Sir, yesterday you mentioned in the webinar that AGV is a continuous time simulation. Like,
Yes, yes. The AGV example I show is actually a continuous time simulation. So actually we are using this approach. We have this discrete time interval here to update that every milliseconds or seconds, how much position this AGV will move. Yeah. Yes,
but
right. That one is
but
using this concept.
but sir, uh, like why do we want to do it on the basis of time when AGV is defined, like all the states are very much defined, like it will pick the load, it will move left, right. So why it is continuous? Why not discrete?
No, if you consider movement of the AGV, okay, I think, yeah, this is some very interesting problem is that if you consider AGV, I should see that the mechanism of the, I mean, especially if you look into a steering mechanism, it's a continuous. If you think about how to control, I mean, how to like drive, or maybe not AGV, just a car, how to drive a car, it's actually continuous. I mean, when you step at a pedal, the accelerator, it's a continuous process, right? You cannot say that when you step on it, only after you step to certain degree, then you start to have an effect. No, at the time you
Oh,
touch the pedal, give some pressure, then the car start to move, right? So this
yes,
actually continuous. It's a continuous
yeah,
control. So AGV will be the same thing. If you start to
okay,
move, then we start to steering like turn the steering wheel, then we see that start to change the gesture of the AGV. Okay, the position start to change. It's not to say that until you move the steering wheel up to certain like position, then you start to see the HV turn. No, at the time you turn
okay,
it, yeah, it's already start to move. Okay, so this, if you look into the physics, the steering mechanism of the HV is a continuous. Okay, but what is a discrete? Is the controlling, the automation, the controlling of the AGV is a discrete event driven. Why? It's because only when this AGV reach a certain status, for example, when they reach a sensor, start to sweep on the sensor, then you start to like sense some like a signal. Only when the signal is received, then you start to do some like adjustment to update certain value. So the controlling will be the same. So if the AGV reach certain position, then I will instruct it to start to turn to another direction. Okay, so this a command or this updating of the running state to the computer system is actually discrete. So this is the part we need to differentiate whether you are analyzing a decision or whether you are analyzing a so-called electromechanical system. So if it's an electromechanical system, it's continuous. But if you're analyzing a controlling system, a man-made system, is like the controlling of this AGV, then it is actually discrete event. But just now you said the electromechanical system is also man-made. Yes, I mean the car is man-made, but all the component, how the electron passes effective, how the it's accelerate actually follow some natural rule, and this rule is not man-made. Okay, because of that, then it's actually electromechanical system follows this natural rule, so that it's actually a continuous system. So this will be the difference. Yeah, but
Okay, sir.
on the
Okay.
other side, the controlling rule of the AGV is man-made. So this is actually
Yeah.
something I'm talking about.
Okay. Okay. Okay,
Okay.
sir.
Yeah.
Okay.
Yeah. Hope
Yeah.
this is clear for you.
Yes,
Okay.
sir. Yes, sir.
Yeah. Okay. So I think it's about the time. It's 6 o'clock now. So I think the pace is just right. Any more questions from all of you? The rest of you, maybe? Or maybe Monica, you still have any other questions?
No, 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 sir. Let me
Okay.
try this. Maybe next time I can ask.
Yeah. Okay. So in that case, I think probably just let's end this session. Though let's continue next Monday lah. So I will start talking about the queuing system. But before that, I think better also look into the questions, the slides are sent into the in the group. So maybe the next time we can starting from here like event graph. Probably I think event graph I can talk about next time when we talking about the queuing system. We start to use the simulation tool here to build a simple queue. Okay, so yeah, so let's resume next Monday.